What we're going to do now is look into the Doppler effect of a moving source and see what the equation for that one might look like. And we're going to start off with our source. Here it is. Not quite sure why I got that little straight line, but there's our source. And I'm not going to draw the waves just yet. What I'm going to do is I'm going to indicate that there is a movement, a velocity for this source. Right? So we have a velocity for the source. And after a certain amount of time, it gets to here. And then after a similar amount of time, it gets an equal distance further ahead. And another similar amount of time, another equal distance further ahead. And so on. And so it just keeps moving ahead further and further. And I'm going to call this one, and this might come back to bite me because I might not make my waves big enough. But let's call this one wave 1, wave 2, or point 1, point 2, point 3, point 4, and then point 5. And I'm going to draw the waves in, and I'll draw them in orange, I suppose. Maybe purple would be fun, or green. We'll go green. So we're going to make our waves green, and right here, point 5 has just gotten to this location and is just about to oscillate. We'll think of it as it's just about to emit a wave, or another wave crest. Let's think of it that way. So I'm not going to draw it. I'm going to draw all the wave fronts that you're going to see are going to be wave crests. So 5 has just gotten to the point where it's about to emit another wave crest, but it hasn't actually done so yet. Number 4, on the other hand, this was where it was the period prior to it getting to 5. So this is sequential. It's moving from 1 to 2 to 3 to 4 to 5. And what we're going to do is we're going to work our way backwards in terms of wave formation. So at 5, it hasn't yet produced the crest. It's just about to. But at 4, it produced a wave there. And it would look something like this. I'm trying to be pretty careful to keep my proportions pretty symmetrical. So this refers to the wave produced by point 4. And I probably should have color-coded each of the points. That would have made it easier. On the other hand, 3 produced its wave earlier. And so what has happened is its wave has had a chance to travel further away. And let me just draw something for us here. The wave travels out in any direction at equal speeds. So I'm just going to indicate this is the velocity of the wave. Okay, so the velocity of the wave is larger than the velocity of the source in this case, by a substantial amount, but the source is in fact moving. Now the thing is that if this is how far, from 4 to 5 is how far the source moves, the wave moves from its point of origin out to this distance in one period of motion. So 3 is going to go out, is going to be out twice as far. By the time the oscillator gets to point 5, the wave produced at point 3 is going to be twice as far out as the wave produced by point 4. So that's going to look something like this. Hopefully I can get this right. Back around there. And so you have a wave that looks like so. And I'll do one more. This is for 3. This one was for point 3. And if I look at point 2, well, point 2 is going to be 3 times further out than the wave produced at 4. So that'll be right around here, let's say. And I should have gotten a ruler out, but it'll be somewhere around here, and down at this point it'll be over there. And then at 2, it'll be something like there, I would say. And so we make the wave. And one of the things that you should see here, and I try to be pretty careful, is the gap behind. So if I look at the distance from 5 to this wave, from this wave crest to this wave crest, from this wave crest to this wave crest, remember that I'm producing a wave crest at the moment at 5. These distances out behind are all the same. the distances out in front are all the same. The difference is that the differences out in front are very different from the distances out behind. And if you have a stationary observer here, the observer is going to experience the waves at a much higher frequency than the oscillator is oscillating at. So maybe the source of the waves is going at 200 hertz, and this person experiences the waves at 400 hertz. Meanwhile, a different observer back behind might experience the waves at 100 hertz. So we're going to get a very different experience. Somebody moving along with the source, let's say that this is a car, and they blare on their horn. Somebody in the car is going to hear the horn frequency of maybe like 500 hertz. An observer standing in front of the car, not necessarily a good idea considering the car is moving forwards, is going to hear a higher frequency, and the observer out behind will hear a lower frequency. And this is why. Because of this wave formation. And I know you've seen this wave formation, and you can look at the simulations and see it, or some of the previous videos. But this is really the description of what causes the wave formation to be as it is. We do not actually get a deformation of each individual wave. For instance, what I mean by this, and I tried to do a good job, but it didn't necessarily work out perfectly. This is a perfect circle. I know you might be snickering a little bit, but it is a perfect circle. And so is this one, and so is this one. There's no deformation of the shape of any particular wave. What has shifted is the structure of the waves in relation to the waves that were previously generated by that same source. So we still have circles. They're still radiating outward at the same speed in every direction. But what has changed is the fact that since the source is moving, they're scrunched up closer in front, and they're spread out further behind. Now the bigger question is, what does this mean as far as an equation? Because we all love the equations. So right now we have a wavelength that is being perceived. This is not the wavelength that was originally intended. That would be if I were to look at from here to here. This would be the wavelength that would be produced by a stationary source. And so what we have then is the new wavelength is equal to the old wavelength minus however far the source goes in the time it takes it to create crests, or in other words, one period. Okay, let me just repeat that again. So the new wavelength is the same as the old wavelength minus however far the source has moved in the time that it takes it to produce one full wave, which is the period. And I can rewrite this a little bit differently. Minus V source divided by the frequency. Okay? So instead of multiplying it by the period, I'm just dividing by the frequency. Now one of the things that we can do is we can do some substitutions. So this becomes the velocity of the wave divided by the detected frequency, or the actual, it's not even just a detected frequency, it's the actual frequency of the waves in relation to each other. Because the waves being closer together but moving at the same speed, and that's this idea here, they're moving at the same speed, but because they're scrunched closer together, the wavelength is going to be smaller, the frequency is higher. And I can substitute in velocity of the wave here divided by f minus velocity of the source divided by f. And what this amounts to then is, if I do a little bit of algebra and rearrange things, I get the new frequency is equal to the old frequency times the velocity of the wave, which I'll just leave as v, divided by the velocity of the wave minus the velocity of the source. Now bear in mind that we've only done the case where the source is moving and the observer is standing in front. Well, if the observer is standing behind, we would expect the frequency that's detected to be less than the frequency of oscillations. And so what we need to do is we need to just rewrite this a little bit once again. Minus plus V source, where the top means toward and the bottom means away. Okay, so we have the detected frequency equals the original frequency of oscillation times the velocity of the wave divided by v minus or plus v source. And because we're looking at the denominator here, if we subtract, the number on the bottom gets smaller. So that causes the number on the bottom to get smaller, which causes the overall number to be bigger. This should make sense, and it should mesh with your experience. When you have a source of sound moving towards you, you detect a higher frequency. So that's why we put the negative sign on top. It's because we want to keep a toward-away structure. In the next video, what we're going to do is look at combining these two Doppler effect equations. It's not so hard. We'll just smush them together, and then we'll look at a couple of particular cases. And hopefully, within the next video or the video after that, we'll get into sonic booms and shock waves.